Previously, when we showcased our initial project at the National Science Fair, we presented Armball Mania, a novel and intuitive sensor-controlled game. This project utilized accelerometer connected to a compact Arduino Nano with serial communication enabling the transfer of orientation data to an Unreal Engine game. The game's objective was to balance a ball on a football field and score goals by manipulating the field's orientation with the accelerometer mounted on a DIY glove worn by the user. The project was a hit at the fair in Kolkata, drawing lines of enthusiastic students and children eager to experience the game. Despite the success, we encountered significant challenges with the accelerometer. The sensor's sensitivity to minute hand movements caused jittery and unstable outputs, making the gameplay less smooth and precise than desired. To overcome this, we decided to upgrade to a gyroscope. The gyroscope provided a remarkable improvement in accuracy, responsiveness, and overall smoothness. After some calibration and optimization, we were impressed by its performance, making the beginning of the next chapter.
During the initial testing phase of Armball Mania Next, we rigorously evaluated the new gyroscope's performance within the original game's framework. Our goal was to access the gyroscope's responsiveness and output accuracy in a familiar environment. Using the trusty old Arduino Nano, we meticulously calibrated the sensor, ensuring it was fine-tuned for optimal performance. To achieve this, we implemented auto-calibration directly into the codebase, allowing the device to adapt dynamically to various scenarios. We delved deep into the existing code, making necessary modifications to enhance responsiveness and smooth out any inconsistencies. Our testing process was comprehensive, involving numerous iterations to identify and resolve edge cases that could potentially disrupt gameplay. As we meticulously tested the gyroscope, we discovered that its precision and stability far surpassed our expectation. Each tweak and adjustment brought us closer to the flawless experience. The gyroscope's capability to provide accurate real-time feedback without lag or jitter was nothing short of revolutionary. This phase of testing was not just about ironing out bugs, it was about refining every aspect of the system to deliver our unparalleled user experience. We were driven by the excitement of seeing our vision came to life and the mystery of discovering how far we could push the boundaries of what its technology could achieve. Every test brought us a step closer to creating a game that was more immersive, engaging, and intuitive than ever before.
However, using the Arduino Nano was not our ultimate goal. While it provided a smoother experience than before, we sought something even faster, smoother, and far more convenient. We needed to eliminate the cumbersome wires and the reliance on serial communication to transmit data. Enter the ESP32, a microcontroller built with in-Wi-Fi capabilities, enabling us to wirelessly transmit data. Transitioning to the ESP32 required a complete overhaul of our code. The previous method of data transmission was neither optimized nor efficient. We decided to bundle the orientation data into a JSON string and transmit it over Wi-Fi. This change not only modernized our approach but also significantly improved performance. The ESP32 allowed us to achieve unprecedented accuracy and speed, making the entire system more convenient. The data now streamed seamlessly over Wi-Fi, reducing latency and enhancing the overall user experience. Getting everything up and running wasn't without its challenges. We spent considerable amount of time ironing out bugs and optimizing the system to ensure the data was transmitted with blistering speed and minimal latency. This involved setting up the socket communication using UDP in Unreal Engine 5, a task that was initially problematic but ultimately successful. We chose UDP because it is ideal for scenarios where speed is paramount, such as real-time gaming.
Previously, our system operated on a feedback loop where Unreal Engine would request data via serial communication and our microcontroller would respond with the XYZ orientation data. With the new approach, our microcontroller continuously broadcasts the data using UDP, allowing Unreal Engine to pick it up as needed. This method proved to be far more efficient and faster as it eliminated the need for repeated request and response. The data streamed effortlessly, ensuring a smooth and immersive experience for the player. This transition to the ESP32 and UDP broadcasting marked a significant milestone to the development of Armball Mania Next. The new system not only enhanced the game's performance but also provided a glimpse into the futures of seamless wireless interaction between hardware and software. Each breakthrough brought us closer to realizing our vision of an intuitive and engaging gaming experience.
After thorough testing, it was time to elevate the game. The previous version was a single-level football field that players could balance, but we aspired to create something far superior. The old, dull, grey graphics were uninspiring. We envisioned a vibrant, visually stunning experience complete with cutting-edge graphics with engaging gameplay. So we decided to build everything from scratch using Unreal Engine 5.
I know that you're coming back home. Know that you're coming back home.
Our first concept was to design a beautiful, soft and cozy room, a pinkish, charming space that felt inviting and delightful. The centerpiece of this room would be a matching pink football field, unlike any field seen before. This field would feature dynamic elements like physics-based animations, hanging decorations, and sophisticated lighting. The entire room would be meticulously decorated to ensure it was not only fun to play in, but also visually appealing. We started by developing all the cute, soft models in 3D Studio Max. Every detail from furniture to decorations was crafted to fit our vision. Once models were ready, we imported them into Unreal Engine 5, where we meticulously textured them, set up the lighting, and placed everything perfectly within the environment. In this updated version of the football game, the room's theme was inspired by a locker room, a fitting choice given the football context. The locker room, however, was not that gritty industrial type one we might expect. Instead, it featured a cute window with potted plants, minimalistic and smooth lighting, and RTX technology enabled to achieve stunning visual effects. The LED light strips hung from the window and ceiling, casting soft, colorful illuminations that interacted beautifully with the walls. A shelf in the distance, slightly blurred to keep the focus on the center football field, added depth to the room. The floating football field in the middle of the room was a masterpiece. It was adorned with charming tile and goalposts that floated with a slight intentional latency, adding a layer of challenge and intrigue in the gameplay. The field was free of traditional markings, emphasizing its whimsical and fantastical nature. The football itself was redesigned to be cute, minimalistic, enhancing the overall aesthetic. When the ball dropped to the ground, it behaved with remarkable realism, its movement governed by advanced physics simulations. This new environment was not only visually stunning but also deeply engaging. The combinations of vibrant colors, smooth animations, and realistic physics created an immersive experience that was both fun and mesmerizing. Every element from the floating goalpost to the soft lighting worked together to transport player into a delightful and captivating world.
With the vibrant environment taking shape, our attention turned to refining the sensors and integration aspect of the project. Previously, our setup relied on 2 breadboards and the tangle of jumper cables to connect the sensors and the microcontroller. This prototypical approach was prone to loose connections and instability, issues that were unacceptable for the polished and production-ready system. We need more robust, reliable solutions for minimize errors and could be presented confidently to both public and potential partners. To achieve this, we decided to move away from the breadboard prototype and create a custom shouldered circuit board. This would involve using single-thread solid core wires and head pins to connect the microcontroller and sensor securely. Head pins are particularly advantageous because they allow us to remove and replace the components as needed, ensuring flexibility and longevity of the setup. This way, the components wouldn't go to waste and could be easily configured for the features iteration on the project. The plan was to solder header pins onto the breadboard, creating a DIY prototyping board tailored specifically for our project. This project would house the ESP32 microcontroller and the various sensors, securely connecting them with single-thread wire running underneath. This setup would not only be more stable but also allow us to detach and reattach the components effortlessly for further experimentation or updates. I began by ordering all the necessary components: header pins, single-thread wires, a soldering iron, and solder. Once the materials arrived, the meticulous process of assembling the circuit board started. First, I soldered the header pins into the place, ensuring they were securely attached to the breadboard. Next, I carefully connected to the headers using single-thread wires, meticulously routing each connection to avoid any potential short circuits. Soldering requires precision and attention to detail. Each connection had to be solid and stable, with no loose wires or cold shoulders joined that could lead to disconnections. Additionally, I had to ensure that no wires crossed path or touched each other, which could cause short circuit and potentially damage the components. This painstaking process involved applying the right amount of solder to each other, then using the soldering iron to create strong, reliable connections. As the circuit board took shape, it became clear that this approach would significantly enhance the project's reliability and functionality. The securely soldered connection provided a stable platform that was far less prone to the issues that plagued our initial breadboard prototype. Moreover, the use of header pins meant that the ESP and the sensor could be easily swapped out or reconfigured, providing the flexibility needed for the ongoing development and experimentation. In the end, this custom circuit board was not only a significant technical improvement but also a crucial step towards making this project production ready. It provided a solid foundation for integrating the sensors and microcontrollers, ensuring that the system would perform reliability during presentations and in real-world application. This meticulous attention to detail and commitment to quality underscored our dedication to creating a truly exceptional product.
After completing the custom circuit board and ensuring its reliability through rigorous testing, we were ready to move on to our next game concept. This new game promised to be both unique and engaging. The idea was to create a scenario where player would defend a kitchen from an invasion of bees. The kitchen would be meticulously designed with a realistic and inviting environment, complete with windows through which the bees would enter, buzzing around the room. The objective was this game was to control a cannon-like gun using our sensor technology to aim and shoot the bees. However, the aiming alone wasn't enough. We needed a mechanism for the firing of the cannon, which led us to integrate a joystick into our setup. This addition would allow players to not only control the cannon's aim with the gyroscope and ESP32, but also the joystick to shoot at the bees, adding an extra layer of interactivity and fun. Integrating the joystick involved some additional planning and modifications to our existing setup. The joystick needed to communicate seamlessly with the ESP32, sending input data that would be interpreted by the game to control the firing mechanism. This meant updating our code to handle the new input and ensuring that the joystick signals were accurately read and transmitted without any lag or errors.
To control the cannon in our new game, we need a joystick for firing while retaining the gyroscope for orientation and movement control. This dual control approach seemed ideal, allowing for a nuanced and responsive gameplay experience. The gyroscope would handle the aiming and the joystick would handle firing, including controlling the rate of fire. To integrate the joystick, I returned to the prototyping board. I inserted another header and carefully soldered and connected the necessary wires to the ESP32. This joystick was a simple module, but it was crucial for the control scheme we envisioned. With the hardware setup complete, I moved on the update of software. I rewrote portions of the code to include the joystick's input. This was not overly difficult as the modular nature of the setup allowed us for relatively straightforward modifications. The data format we were using, JSON, needed to be updated to include the joystick's values. Now, in addition to the gyroscope's XYZ orientation data, the JSON string also contained the XY values from the joystick and the boolean indicating whether the joystick button was pressed. The prototype board now featured the gyroscope, the ESP32 and the joystick, each with its own header properly soldered and connected underneath the wires. This DIY circuit board was designed for flexibility. Each component could be removed or replaced as needed, making it perfect for ongoing development and testing. In terms of wiring, the video shows a single wire connected to the ESP32 microcontroller board. This wire is used solely for uploading code to the ESP32 and powering it during testing. In the final production stage, the device will be powered by a battery, eliminating the need for wire. It's important to note that the wire does not transmit data to Unreal Engine. It is purely for power and code uploads during development. This setup allowed us to seamlessly integrate the joystick with our existing sensor system, creating a robust and flexible control scheme for the game. The joystick's values were now the part of the data stream sent to the Unreal Engine, enabling precise control over the cannon's firing rate and direction. This integration not only enhanced the gameplay experience but also demonstrated the versatility and expandability of our custom sensor platform.
After finalizing the joystick integration and completing the DIY prototype circuit, I shifted my focus back to the 3D environment and modeling of the kitchen environment for our game. We meticulously added various kitchen elements such as cupboards, fridges, shelves to create an authentic kitchen vibe. These details were crucial for immersing players into the game's environment. Looking ahead, we plan to incorporate breakable objects like plates and utensils into the kitchen scene. When the ball collides with these objects during gameplay, they will shatter in real time, enhancing the satisfaction and realism of the experience. Next, we turned our attention to designing the bees themselves. The bees were designed to be cute yet believable, featuring black eyes and a textured body with minimalistic wings. Animating the wings and coding their behaviors to fly around the kitchen area was naturally a fun challenge. We ensured that the bees would move randomly with slight delay, providing players with opportunities to aim and shoot. At any given time, there were 5 bees flying around the kitchen. When a bee was hit, it would realistically fall and disappear, only to be replaced by a new bee flying in through the windows. This spawning mechanism added dynamism to the gameplay, ensuring that players always had targets to engage with. Speaking of controls, the sensor's movement controlled the cannon's orientation. Tilting left or right moved the gun horizontally, while tilting forward or backwards adjusted its vertical position. We intentionally slowed down the vertical motion to add a layer of realism and challenge to the aiming. Meanwhile, the joystick's sensitivity played a crucial role in controlling the cannon's firing rate. Slight movements of the joystick resulted in balls with lower velocity, while pushing the joystick further increased the projectile speed. This sensitivity allowed players to fine-tune their shooting strategy based on the beast's movement and patterns and the game's pacing. Overall, integrating these elements, detailed kitchen environments, interactive bees with realistic physics and responsive control schemes created an engaging and immersive gameplay experience. Each component contributed to making our game not only enjoyable but also challenging, ensuring that players would have fun while honing their shooting skills in the whimsical kitchen setting.
As we approach the final stage of the development, we refined the DIY prototype circuit board to ensure it was user-friendly and portable. Adding a small vibrator was the finishing touch, enhancing immersion through the haptic feedback. Whenever a bee was hit or the cannon fired, the vibrator provided subtle vibrations, heightening the player's sense of engaging and realism. In collaboration with Unreal Engine, signals were set up to trigger the vibrator accordingly, syncing seamlessly with gameplay events. The integration not only added the tactile feedback but also enhanced the overall experience, making each interaction with the game environment feel more lifelike and responsive. With this final adjustment completed, our innovative kitchen-themed game was ready to captivate players with its blend of detailed environment, interactive challenges, and immersive feedback mechanisms. Whether aiming at buzzing bees or admiring the intricacies of the kitchen settings, players were sure to enjoy the dynamic and engaging experience from start to finish.